So now we move to the new section dealing with extremal problems. So in undergraduate graph theory, we define this extremal number, or which is called Turan number. For a given graph, say f, we define extremal number of f as a function on n, which is the maximum number of edges in an n vertex graph not containing f as subgraphs. And we define the TRN as the balanced complete alpha type graph. It is a complete alpha type graph where each color class has size as equal as possible, and small t of n be the number of edges in such a graph. And Turan theorem says that the extremal number of k sub r plus 1 is exactly t sub r n, and this Turan graph, the balanced complete alpha type graph, is the unique graph with the equality, with this many edges having no complete graph of r plus 1 vertices. And we can generalize this to hypergraph. So we write R graph, meaning that it is R uniform hypergraph. So instead of, graph G is a collection of vertices and edges, where edges are subset which consists of the pair of the vertices. And we consider H is an R uniform hypergraph if each edge is a collection of sets of size R. And we can similarly define the extremal number for R graph. So R uniform hypergraph, we shorten for R graph. 2 graph is a graph. For an R graph F, we write extremal number of NF be the maximum number of edges in an n vertex R graph. Not containing f as a subgraph. Sometimes to denote that the hypergraph is R uniform, we write this superscript R with a round bracket. So we have this Turan theorem determine the extremal number or Turan number of a complete hypergraph, a complete graph. Then we can consider this number for other graph or other hypergraph. One of the easy graph we can prove the bound is that we know actually the extremal number of K22, which is a cycle of length 4, is at most this. So roughly half times n to the 3/2. We can prove this upper bound. So, in order to determine or estimate an extremal number, the extremal number of a graph, you have to prove two things. You have to prove an upper bound and lower bound. For upper bound, what do we have to prove is that if we have a graph with more than this number of edges, with the n vertices, then you should be able to find the graph here. That proves an upper bound. For the lower bound, if you want to find some lower bound, then you need to construct a graph with this many edges. That has no copies of K22 in there. This graph that you want to prove. Then K22, this upper bound can be proved in a not too difficult way. So let's say m is the number of edges. And we want to show that if we have a graph with more than this many edges, then we have a K22. Or in another word, if we have a graph with no K22, then it has less than or equal to, this many edges. So let's prove that if we have a graph with no K22, then we can get this upper bound. So what we do is we count the number of copies of K12. So K12 is same as P3. So it's a path of 3 vertices. So how do we count it? We choose a vertex which is gonna be play the role of this middle vertex. In G, we choose one vertex which will be this, and then choose other two vertices. And we count them. Middle vertex, we choose it from G. We know that the number of K12 is how many? For each vertex, if that's the middle vertex, you have to choose 2 of its neighbor. Then you get a copy of K12. So this gives you the expression. But what we know is that here we have this function. We add by n. So each function is essentially x choose 2, which is x squared minus x, which is a concave function. And by convexity, what we know is that if we have a convex function and we have a and b, then the fa plus fb is at least twice times fa plus b over 2. So that's kind of definition of convexity. You can generalize this 2 into more number. So here you add n terms. So by applying this convexity, it's actually same as that you take the average value and then you apply to this function and then you multiply n. This is by convexity, and by degree sum formula we know that this is twice the number of edges over n, choose 2, which is 2m squared over n minus m. So why did we count this K12? Is that the 2 copies of K12 putting together is same as K22. So if G has no copy of K22, then the above number must be at most n choose 2, because for each copy of K12, we count the U and V. We write this U and V, this set. And we, for the next copy, we again write these two vertices, say X and Y, and so on. If ever we write the same set twice, meaning that for given U and V, there is one copy of K12 having this as a non-middle vertex, and another copy of K12 having this as a non-middle vertex, then we get a copy of K21. So all this set must be all distinct, but there are at most n choose too many such sets, so this must be at most n choose 2, because otherwise we can find two copies of K12 with distinct middle vertex sharing both ends. And which produced a copy of K22. So what do we get? We get m 2 times m squared over n minus m is m mod n choose 2. This implies that m is m mod n over 4 times 1 plus square root of 4n minus 3. So this gives us an upper bound. So later we will learn about the lower bound, and we actually learned about lower bound in undergraduate graph theory, but we will partially repeat. Later we will, also generalize this to not just K22, but this argument also yields an upper bound for KST for, other S and T. So now now let's consider some Turan numbers of hypergraphs. So let H be a hypergraph, R graph. With alpha times n choose R edges. Then let's say H has density alpha, and for an R graph F, let pi of F be the limit when n goes to infinity, the extremal number of nf divided by nr, and let's call Turan density. So if this value exists, then let's say this is the Turan density. Then, first we define this, we need to check whether, it is actually well defined, whether the value of this exists. So Katona, Nemeth, Simonovich actually proved that for any R graph F, this pi of F exists. And for that, what we have to show is that if you consider this sequence, and we just need to show that this sequence is monotone. For example, if it's a decreasing sequence, then it is bounded. It's between 0 and 1. So as long as this is a decreasing, then it must converge. So for that, I mean, we need to think about the relationship between the extremal function on n vertices and n minus 1 vertices. So suppose that H is an R graph with say alpha times n choose R edges having no copy of F. So what we do, we randomly delete a vertex to obtain an R graph H prime. Then what do we get? The expected number of edges in H prime is as follows. Each edge and n vertex, each edge has R vertices. As soon as our random vertex is picked from here, then this edge disappears. And otherwise that edge remains. So that the probability that each edge remains is 1 minus R over n. And there are exactly R times n choose R edges. But with some computation, we know that this is exactly alpha times n minus 1 choose R. So there exists V such that H minus B still has density at least alpha. So expectation is this much, means that there exists a choice which does better than or equal to the expectation. So moreover, as H prime is a subgraph of H, this does not have any copy of F. So there exists an n minus 1 vertex graph, vertex R graph, with alpha times n minus 1 R edges having no copy of F. So what does this show? This shows that this sequence forms a decreasing sequence. Of real numbers in between 0 and 1. Because such an existence of H prime such an existence of F is same as this for n. If you have this alpha value for n, then you take that as an alpha and consider this H, and that shows that there is alpha prime. So for this, in this sequence, the nth value and n minus 1th value, if you compare them, then the n minus 1th value is as large as nth value. So it is actually a decreasing sequence. So to be more precise, non-increasing. So this shows that this density exists. And next, what we want to prove is that so once we have this then it's natural to decide, which graphs, the Turan density of, graphs or hypergraphs. For graphs, we know quite a bit, but for hypergraphs, not much thing is known. But one of the things that Erdish proved is that any R-partite R graph has Turan density 0. So, for example, if you consider a graph, then R is 2. Any bipartite graph has a Turan density 0. So Turan density 0 does not necessarily mean that the extremal number is 0, but in graph case, it means the extremal number is subquadratic, because this is quadratic in polynomial in n, and if this is subquadratic, then this goes to 0. And for R uniform case, then the power of this, this extremal number is, n to the something which is smaller than R, or, this is little of n to the R. So that's what it means. So what Erich exactly proved is that for given R and S, and say n is big enough, we have that extremal number of n and complete graph on R vertices with S vertices on each set is at most n to the R minus 1 over S R minus 1. So which is so for fixed n and R, this is real of n to the R, which is growing much smaller than n to the R. So if this is true, then for given f, which is R-partite R graph with say f many, so this has s many vertices, then this is R-partite R graph, so this is a subgraph of some complete graph on R parts. R parts, and each of them has S vertices. So just like the for bipartite graph case, if you have some bipartite graph, say F, then what you take is that you take some, this is S vertices, then you take at most 6 vertices here, and then you embed this to here, and then this to here, and this is complete bipartite graph. Then this F is always subgraph of complete bipartite graph with a certain number of vertices on each side. By the same way, this F is always a subgraph of R uniform hypergraph with part size S and S, each part size S for some S. And this means that the extremal number of NF is at most extremal number of N KR S. So as soon as we prove this, then we automatically that any R-partite R graph has Turan density 0. So this is something that we will prove in, next time.